Hi everyone, let me introduce myself. I'm Kishan Jeeveswaran. I'm working as a deep learning researcher at Navinfo Europe in the Netherlands. Today, I would like to present my research paper titled A Comprehensive Study of Vision Transformers on Dense Prediction Tasks. As you all are aware, convolutional neural networks' remarkable performance has made them the prominent choice of architecture in computer vision tasks. On the other hand, the transformers have become dominant in NLP owing to their ability to learn long-term dependencies via self-attention. The recent breakthrough of vision transformers in image recognition motivated the vision community to apply them on other dense prediction tasks. Vision transformers have achieved compelling performance in these applications, and thus they have become an alternative architectural paradigm. However, the mechanism by which VTs process the images is significantly different from that of CNNs. The receptive field progressively increases in CNNs, whereas transformers split the image into patches, embed them into tokens, and globally attend to them at every layer. CNNs have inherent inductive biases such as locality and translation equivariance, whereas transformers lack these inductive biases. Hence, the choice of these two architectures comes with their own merits and limitations, and the unique working principles of transformers raise many questions about their generalizability, robustness, reliability, and reliance on texture. Although few of these questions are addressed in the image classification domain, they have not yet been fully addressed for complex dense prediction tasks. Therefore, in this work, we do a comprehensive analysis of vision transformers by comparing them against CNN backbones as feature extractors for object detection and semantic segmentation. Now let's talk about how we modified the vision transformer architecture as feature extractors for dense prediction tasks. We chose data efficient image transformer DEIT as the transformer backbone. DEIT processes the input image as a set of tokens and repeatedly applies self-attention blocks to learn the relationships between them at every layer. In addition to these tokens, they append a class token to infer the class label and a distillation token to distill the knowledge from another model in image recognition task. We remove the class and distillation tokens and reshape the remaining tokens into a feature map of size 32 cross 32 cross k, which we call FM2 here in this diagram. Additional feature maps are created by upsampling and downsampling the feature map as shown in this figure. For object detection, we use fully convolutional one-stage object detector (FCOS) as the detection head, which is an anchor-free approach. The detection head will be shared among different feature maps as shown in this figure. And for semantic segmentation, we use a lightweight segmentation head to infer dense pixel-wise classes. Let's move on to the performance comparison for in-distribution data. The experiments are conducted on both detection and segmentation tasks for VT and CNN backbones of different network sizes. As you can see in the table, we use 3 DIT variants and 3 CNN counterparts with the comparable number of parameters. For detection, we use the COCO dataset, and for segmentation, we use COCO stuff. The table compares the performance of transformers and CNN backbones under different evaluation metrics. As you can see, vision transformer based architectures outperform their CNN counterparts with less complexity. However, VTs have slower inference speed with more energy consumption. Since vision transformers are new to the community, the hardware might not be optimized for this architecture yet. We believe that VTs can infer faster if the GPUs are optimized for them. We saw the results on in-distribution data, but the models should be able to perform well on unseen data as well. We chose Berkeley Deep Drive as the out-of-distribution dataset for our analysis, as it constitutes of road scenes with traffic elements. We train the models on COCO and evaluate them on BDD dataset. The results show that vision transformers outperform CNNs on the out-of-distribution dataset for both detection and segmentation tasks. At times, transformer backbones outperform significantly larger CNN backbones. For example, in segmentation, DIT tiny and DIT small outperform ResNet 50 and ResNet 101 backbones. This indicates that the features learned by VT backbones are more generalizable. It is shown in the literature that robust and generalizable models often converge to flatter minima in the loss landscape. If models find solutions in flatter minima, the performance would not change significantly when the weights are perturbed. Meanwhile, if the models converge to a sharper minima, even a slight perturbation in the weights could result in drastic change in performance. In this experiment, we probe the loss landscape of VTs and CNNs by adding noise with increasing strength to trained models' weights and evaluate them on a subset of the training data. The graphs clearly show that VTs perform better than CNNs through different strengths of model perturbations. This could explain why they generalize better to out-of distribution datasets. This goes in line with the results we saw earlier for out-of-distribution performance. Vision transformers attend globally to the image at every layer. Ideally, this should facilitate them to handle larger inference resolutions better than CNNs. In order to test this hypothesis, we use the models trained at 512 x 512 resolution to infer at higher resolutions. It is worth noting here that we interpolated the positional embeddings to adapt VTs to infer at higher resolutions. The graphs show that CNNs perform better than VTs at higher resolutions in detection. However, in segmentation, higher inference resolutions has similar effect on both VTs and CNNs. We believe that the interpolated positional embeddings might not be as effective for detection as they are for segmentation, and we leave cross-task suitability of interpolating the positional embeddings for future work. Deep neural networks that are being used in safety-critical applications such as autonomous driving are expected to be accurate and reliable. In order to study the reliability of predictions made by VT and CNN backbones, we compare the calibration errors in this experiment. Calibration error quantifies the mismatch between the predicted confidence and the actual accuracy of the models. The models would be more reliable when its predicted confidence matches the actual accuracy of those predictions, and consequently they would have less calibration error. As can be seen in the table here, VTs have lower calibration errors and are better calibrated than their CNN counterparts in both the tasks. Studying the robustness of a model to different noise in the data is important when deploying them in an ever-changing environment. In this experiment, we apply 15 different natural corruptions such as brightness, fog, and motion blur on the evaluation set and compare the performance. The heat map indicates the absolute performance of VTs and CNN-based architectures. Higher performance is indicated by darker shades. It is clear that transformers perform better than CNNs, and we can attribute this to their global receptive field, which helps them attend to salient and faraway regions in the image, making them more robust to pixel-level changes caused by corruptions. Similar to natural corruptions, the model should be robust to malicious transformations such as adversarial attacks. We conduct untargeted adversarial attacks with increasing strengths and compare the performance of VTs and CNNs in this experiment. We could see from the graphs that VTs are robust in general, and in segmentation, CNNs outperform VTs at higher attack strengths. In addition to untargeted attacks, we conduct targeted attack by swapping the person and car classes. The table shows percentage drop in the model's performance and F1 scores. VTs generally retain a higher percentage of their original AP and F1 scores compared to CNNs, and we believe that the dynamic nature of the attention modules in VTs makes it harder for the adversarial attack to find successful gradient directions to fool the network. Moving on to the texture bias analysis, recent studies have shown that models which focus more on the shape-related features are more robust and generalizable compared to the models which rely on texture of the objects. In this experiment, we stylize the images with texture of another object which is not present in the image and extend the texture bias analysis from image recognition to object detection and semantic segmentation. Figure on the left shows an example of stylization. We apply a texture of a zebra on an image with a person in it. A texture-biased model would misclassify the person as zebra, so having less texture bias is preferable. The table, the table on the right shows texture bias values for VTs and CNNs, and SC in the second column of the table corresponds to texture bias numbers when the COCO supercategory classes are taken into account. We can see from the numbers that the model prediction changes even more within the supercategory when it is stylized. Overall, VT backbones have lesser texture bias compared to CNNs. In addition to the texture bias analysis, here we evaluate the performance of the models with increasing strengths of stylization and see that transformers rely less on texture cues compared to CNNs to make their predictions. We attribute their less texture bias to the global receptive field, which helps them rely more on global shape-related features than local texture cues. In conclusion, let me sum up the main observations from our experiments. Vision transformers outperform CNNs in distribution dataset. Despite lower computational complexity, they have lower inference speed. We believe that if the GPUs are optimized for transformer architectures, they have the potential to become dominant in computer vision. We saw that VTs generalize better to out-of-distribution datasets than CNNs. Our loss landscape analysis shows that VTs converge to flatter minima, which can explain their generalizability. Based on our analysis on calibration error, we also saw that VTs are better calibrated than CNNs, which makes their predictions more reliable for deployment in real-world applications. Moreover, we find that the choice of architecture plays the primary role in determining its calibration. Although VTs have global receptive field, their performance degrades for higher image resolutions. We believe that the interpolated positional embedding might be the reason for their performance degradation. VTs are more robust to natural corruptions and adversarial attacks compared to CNNs. They are also less texture biased. We believe that this could be attributed to the global receptive field as well as the dynamic nature of the self-attention. We hope that our analysis would help the vision community to make an informed choice based on the vision application. That concludes my presentation. Thank you for your attention. Now I am happy to answer any questions you might have.